Hey everyone. I want to continue talking about permutation groups, although we're going to take what feels like a little bit of a detour now. So let's look at our next definition. And so let's see, let's take a couple of groups. So let's let G and G prime be groups. A function which I guess I'll use an H from G to G prime such that H of xy equals H of x times H of y for all little x and y in G. This has a name, it's called a homomorphism. This is one of the most important definitions that you're going to get in abstract algebra. And so, first, let's just take a look at this. This looks very similar to our definition of isomorphism. What's the difference? Well, an isomorphism is a bijection that satisfies this property right here. So now what we can say is that an isomorphism is a bijective homomorphism. So it's a little bit stronger. And homomorphisms, this is a key feature in the study of both groups and next quarter when we study rings. Homomorphism is an extremely important concept. In fact, when it comes to group theory, if you want to say what is group theory, it is the study of groups and their homomorphisms, right? So the two really go hand in hand. So what is a homomorphism then? It's a function that is not necessarily one-to-one, not necessarily onto. It's just a function that respects the operations of G and G prime, right? So it's an operation respecting function. And then so I'll just put this in parentheses. So an isomorphism is a bijective homomorphism. Let's start off with some facts. So we haven't changed chapters. We're still in chapter 8, which is the study of permutation groups, but it's time to sort of get a little bit more advanced technology so that we can study both permutation groups and other types of groups a little more closely. So let's let H from G to G prime be a homomorphism three parts to this. So the first one, if little g is in capital G and little n is a natural number, then h of little g to the n is equal to h of g all raised to the n. Right, so this first part of the lemma then says that you can apply exponentiation inside the parentheses or outside and you'll get the same result. Part B, h of the identity e equals, now I need to use another symbol, so I'm going to use the e prime. So this e right here stands for the identity in G. This one here stands for the identity in G prime. And then part C. What do I want? Oh yeah, if G is in capital G, then H of G inverse is equal to H, or it's equal to the inverse of H of G. That's, I guess, the way to say it. Okay, so we have three facts that we want to verify, and these sort of get at the heart of how homomorphism behaves. Now, I'm about to erase this, but let's just take a look at what this is saying. So what this is saying is H applied to G times G times G times G, a bunch of G's inside, is equal to H of G times H of G times H of G times H of G. That should not be surprising given this homomorphism property right there. So in fact, for the proof of part A, and I'll write this down and then I'll erase it, the proof of part A is just induction, where the definition gives us the base case, right? When n equals 2, we would have G times G. Well, H of G times G equals H of G times H of G by definition of homomorphism. And then the proof of the rest of part A just follows from induction. So I'll let you put the details in for that. For part B, so let's see, what do I need? Okay, so now I want to show that H of the identity in G is equal to the identity in G prime. So let's see now, H of E is equal to H of E, H of E times E, right, because E is equal to E times E. Now our homomorphism property allows us to break this up, and let me do a little bit better here. So let's say note that H of E is equal to H of E, which is equal to, now we can break this up, H of E times H of E, and now I have this equation, right, where the left-hand side is H of E and the right-hand side is H of E times H of E. And now we can apply cancellation. So applying cancellation, and I still don't know how to spell cancellation. It looks funny with 2 L's, but then it also looks funny with 1 L. So applying cancellation, so I'm going to multiply, or I guess I'm going to cancel on both sides of the equation. I can cancel on the left or the right on this side. And what do we get? We get H of E on the right-hand side, and on the left-hand side, we are left with E prime, the identity in G prime. Okay, so that's what we need. So applying cancellation, let me say this better. Also, we have H, or E prime is equal to H of E. Okay, so now moving on to part C, I want to show that inverses are taken to inverses. So, let's see. I guess let's say observe that, I mean, this is basically just a computation now. E prime is equal to H of E, so that's from part B, which is equal to H of G times G inverse, right? So we have this element G. We know that G times G inverse has to equal the identity. Now let's split this up, H of G inverse. And so now we need to look at this equation right here and notice what's happening. We have H of G times this element right here, and we get the identity. Well, that can only happen if the thing we multiplied by right there is the inverse of H of G. So this implies that H of G inverse is equal to the inverse of H of G. And so that completes the proof of that lemma right there. As a quick corollary, so notice what we have. We have, well, okay, let me write down what we don't have. So corollary, this would be 8.4. If H from G to G prime is a homomorphism, and G is an element of capital G, then H of G to the N is equal to H of G raised to the N for all N in Z. So notice the difference. Part A of our theorem just said that it was true for N in the natural numbers. And now we can extend this to all integers. And how does that work? Well, we know it's true for positive integers. We know that it's true for N equals 0 for part B. And we know that it's true for N equal -1 from part C of our previous lemma. And so now, combining that together, what we get is that it's true for all integers. A quick piece of notation, standard notation. You don't even need to write this down, but it's just, I want to contrast what your book does with what most other people do, including myself. So standard notation, if f is a function from, let's say, a to b. So this is just function, not necessarily homomorphism or anything like that. If we have a function and C is a subset of A, right? So a subset of the domain, then f of C is equal to, right? So this is the notation for the set of all possible outputs. So the set of all things in the form f of little c, where little c runs through all elements of capital C, right? It's the image of the set. So this is the image of C. Your book does things a little bit differently. And so I just want you to be aware, what they will write is f of square bracket C. I don't know why, but that's what he does. So when you see in your book f of square bracket C, all that means is the image, right, of the set C under the function f, right? It's exactly this same set right there. So just be aware of that as you're working through. When you see that f of bracket C, there's nothing deep going on. It's just his notation for the image of a set. And I really don't know why he does that. Right? Most authors, I've seen it in a couple other situations, but for the most part, people just write f of C without bothering with the square brackets. Okay, so the next thing, so this will be lemma 8.5. This is more properties of homomorphisms. So let's let H be a subgroup of G, and little h, let's word this a little better. Let H from capital G to capital G prime be a homomorphism, and let H be a subgroup of G. Two parts to this, right? And so what this is going to tell us is that homomorphisms behave nicely with respect to subgroups. So part A is that H of capital H is a subgroup of G prime. So homomorphisms take subgroups to subgroups. All right, so that's a big deal. That's nice. And part B, if little h is 1-to-1, then H is isomorphic to the image H of H. Nothing really surprising going on there. Right, so really, I mean, there's nothing to prove for part B once we know part A. So let's get the proof of part A Okay, so I need to show that H of H is a subgroup, which means that I need to apply the subgroup test. So since E is an element of H, we have E prime, which is equal to H of little e, is an element of H of capital H. I just used, so this is, what was that, lemma 8.3 part B, that H of E is equal to E prime. Therefore, H of capital H is non-empty. Okay, so now I can apply the subgroup test. I'm going to choose a couple of elements in H of H. So let's pick, let's say now, choose, or let, a couple elements. How about X and Y be in H of capital H? I need to show that H of capital H is closed under both multiplication and inverses. So let's see, if they live in H of H, so then there exists, let's say, an A and a B in capital H, such that H of A is equal to X, and H of B is equal to Y. So then, okay, what does that mean? What am I trying to do? I would like to show that X times Y lives in H of H. So let's look at X times Y. That will be H of A times H of B. And now we know we've got a homomorphism, so I could join this into one piece here, H of AB. And since AB lives in H, capital H, little h applied to that has to live in H of H. So the fact that capital H is closed forces us to conclude that H of capital H is closed under multiplication. What else? So let's look at, who do I want now? X, so let's do X inverse. Also, X inverse, X inverse is equal to H of A inverse, which is equal to H of A inverse. And since A is in capital H, so is A inverse. And so that tells us that this is in H of capital H also. Okay, so by the subgroup test, so by the subgroup test, H of capital H is a subgroup of G prime. And then for part B, okay, so now what we want to do is say, assuming that we have a one-to-one function, or one-to-one homomorphism, it takes H, or H is isomorphic to H of H. So we just say, note that, so now I need the isomorphism. So note that H, little h, restricted to capital H from H to H of H is an isomorphism. And there's nothing surprising here. H was already one-to-one. If we assume that little h is one-to-one, it is then onto its image, and H itself has the homomorphism property, so now we have a bijective homomorphism. Right? And that's exactly what we need, an isomorphism. Oh, it's so hot in my office today. I was tempted to turn the fan on, but it might be too loud for you to hear. How are we doing on time here? 20 minutes? Okay. Okay, so I want to do one more. Well, we're going to finish this chapter with a sort of famous theorem. I said that permutation groups are an important class of groups when it comes to the study of group theory, and this theorem is really going to tell us why. So this next theorem actually has a name. So this is theorem 8.6. And it's called Cayley's theorem. It goes like this. Every group is isomorphic to a group of permutations. That's pretty amazing. I mean, what that tells you then is that really, if you want to study groups, all you need to do is study all the groups of permutations, because every group is isomorphic to a group of permutations. The proof is pretty fun, but you got to pay attention here. There's a little bit of, not trickiness, but you have to understand, you have to follow the notation. So let's let G be a group. And so what we're going to do is we're going to find a group of permutations for which this capital G is isomorphic to. Now, for each little g in capital G, we're going to define, so this is going to be, I'm going to use the notation tau sub g. So tau sub g is going to be a function from G to G. This is not necessarily a homomorphism or an isomorphism, it's just a function. In fact, we'll see that it's definitely not a homomorphism. So we're going to define this function right here by tau sub G of little x is equal to G times x. This function has a name. I don't know if I need to want to tell you what the name is. I'll tell you at the end of the proof. I'll give you the name rather than clouding up the proof with the name, because it's kind of long. But I'll just say it out loud. So this is called the left regular representation of G. Okay, so here's our function, right? For each little g, we have one of these. So let's see what we can say about this. So, suppose that tau sub g of x is equal to tau sub g of y. All right, what does that mean? Well, then we have gx is equal to gy, and now I can apply cancellation, cancel the g's on the left-hand side, and that conclude that x equals y. So x equals y. Here I'm just doing cancellation. I don't know, what do you think? 1L? I think 1L is probably better, but I don't know. Sometimes they both look weird to me sometimes. What did I just show here? I just showed that tau sub g is 1 to 1. If you say thus, tau sub g is 1 to 1. Also, now, given, let's pick somebody in G, given, I don't know what to call it, little h in capital G, note that, so I need to fill in the blanks here. Tau sub G of somebody has to equal h. Who is the element that I can put in here that actually satisfies that? Well, think about the definition. Whatever you put in the parentheses gets multiplied on the left by G. If I want an output of H, then the right thing to put here is G inverse times H. Therefore, what did I just show? I chose somebody in the codomain. I produced somebody in the domain that gave me that output. So therefore, tau sub G is onto. So what we have for every little g, tau sub G, is a bijection from G to G. What do we call such things? Well, we call them, what? Permutations, that's right. So conclusion, for every little g in capital G, we have tau sub G is a permutation of capital G. In other words, tau sub G is an element of S sub G. Okay, now what do I want to do? Well, I'm trying to produce a group of permutations that is isomorphic to capital G. All right, so that's where we're headed. And so, let's see, what do I need next? Yeah, let's define a function h. Oh, I shouldn't have used little h. Let's use phi now, since I used h in the proof already. So let's define phi from little g to S sub G, the group of permutations of G, by phi of little g is equal to tau sub G. So make sure that this makes sense to you. The input is an element little g. The output needs to be a permutation of G. The natural thing to do is to choose that particular permutation of G. And now I need to verify that phi is a homomorphism. So given, let's say G and G hat in capital G, we have phi of G times G hat is equal to tau of G, tau sub G G hat. That's the formula. Now, tau G G hat of little x is equal to G G hat times x, which is equal to G parentheses G hat x. That's equal to G times tau sub G hat of x. So you got to kind of keep your head straight, but just one by one I'm applying the definitions of tau sub G and tau sub G hat. And then this is equal to tau sub G of tau sub G hat of x. And so tau sub G G hat is equal to tau sub G times tau sub G hat, where times here means composition of functions. Since phi of G hat is equal to tau sub G hat, we can now put this together. So notice what we have. We have this equation, we have this equation, and then this connects them in the middle. So we conclude that, let's see if I can fit it here, phi G G hat is equal to phi of G, phi of G hat. In other words, phi is a homomorphism. So therefore, phi is a homomorphism. Okay, what's next? So now I have a homomorphism from G to S sub G. The next thing I'd like to do is show that it's 1-to-1. And then I'm going to apply our previous, I guess that would have been lemma 8.5 part B to get the isomorphism. So now suppose that phi of G is equal to phi of G hat. For some G and G hat in capital G. Given little x in capital G, we have, so let's see, tau sub G equal to tau sub G of tau sub G hat. That's because of this. And so tau sub G of x has to equal tau sub G hat of x. Right? They're the same function, so they got to do the same thing to x. Now it follows that gx equals g hat x. And now if we do right-hand cancellation, right, so by cancellation, g equals g hat. Therefore, or thus, phi is 1-to-1. Okay, so now we've got a 1-to-1 homomorphism from G into S sub G. According to our previous lemma, part B, that means that G is isomorphic to its image inside S of G. So by lemma 8.5, G is isomorphic. G is isomorphic to H of G, and H of G is a subgroup of S of G. That completes the proof, right? What we have then is G is isomorphic to a subgroup of permutations of G. Okay, so now let's actually say the name of this. So phi, so that's the end of the proof, but now a little piece of terminology. Phi is the left regular representation of capital G. Right, so it's got a special name. That is an isomorphism from G into a group of permutations, and it happens to be a group of permutations of G itself. Let's try a couple of examples. So first example, let's let H from Z to the group of permutations of Z be, oh, I've been using phi, so let's use phi, sorry, let phi be the left regular representation of Z. So then, for example, sorry, I keep using h, it's phi. Phi of 5 is the function tau sub 5. So what does tau sub 5 do? It does 5, it applies the operation with 5 to any element of x. So if we do, tau sub 5, in general, tau sub 5 of n, that's going to be 5 plus n. So it adds, because plus is the operation in z, it adds 5 to any element that you plug into the function. Try one more example. Let's let V be the Klein 4 group. And let me just remind you by writing down the table real quick. So E, A, B, C, E, A, B, C. E, 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 E. A, B, C, A, B, C. And I think, what do we choose here? Oh, we got to choose it to be C, right? Yeah. C goes there. B goes there. A, C, B, and A. Okay, so there's the Cayley table for the Klein 4 group. And then I just want to play around a little bit with the left regular representation. So let's let phi from V to S sub V. And remember who S sub V is? S sub V, V has 4 elements in it, so this is isomorphic to the symmetric group S sub 4. But that's sort of beside the point right here, so this is the left regular representation. So let's see. Tau sub A of E, what's that going to be? Well, it means A times E, and so that just gives us A. I just want to do a few different examples. Tau sub A, I guess I'll do tau sub A's all the way. Tau sub A of A, that equals A times A, and then if we look at the table, A times A equals E. Tau sub A of B, that's going to be A, B, which is C, right? A times B is C. And then tau sub A of C, that's A times C, which has to be B. Now, one thing to be aware of now, what do we have? We have phi takes V to a subgroup isomorphic to S sub V. Since S sub V is isomorphic to S4, what we can conclude is that S4 contains a subgroup isomorphic to V. So that's kind of fun. So one thing to take away from here, I don't want to say this, well, I guess I'll just say it. S4 contains a subgroup isomorphic to V. So that's kind of nice because it's going to be a pain. In fact, we want to come up with various ways to think about the Klein 4 group. But one way that we don't really want to have to deal with is writing down the table all the time. So now, if you go to the I can't remember what page is on. Let me look it up real quick. It's page 80 in the book. So page 80 in the book has the subgroup lattice for D4. And I believe, well, yeah, if you look closely, what you'll find, well, yeah, okay. Yeah, if you look closely, what you'll find is a subgroup in D4 that's isomorphic to V, and because D4 is a subgroup of S4, you'll have a subgroup of V sitting inside, algebraically sitting inside S4. Okay, so that's a good place to stop, and we're going to start a new chapter next time, so we will see you then.